I want to start this video by going back to the little chart that I displayed previously, and I just want to go through the first several of these complementary perspectives whenever we're designing an application, and the little definitions next to them. The first one we called an application a set of interacting objects. Okay, an object is an implementation of one or more roles. A role is a set of related responsibilities, and a responsibility means that there's an obligation to perform a task or to have or possess or know some form of information. And so in this lesson I want to talk about the last two there that I pointed out, the ones in the middle, a role and the responsibility. So like the chart said, each object plays a role, it plays a part of a larger conceptual machine. In other words, we delegate one or more responsibilities to an object, and it now has the obligation to take care of that task or to hold that information. So we're depending on it to do its job so that the machine as a whole can function correctly. If it doesn't do its job, then the machine, we would expect it to have issues. So we have a need, and we delegate the responsibilities to take care of that need to an object. Now, if we return to the assembly line metaphor that I established in the second video, consider the various parts of a factory that we might be familiar with. There are machines like conveyor belts. These will move things across great distances from one area to another. There are different kinds of robotic arms. The robotic arm that I'm thinking of right now can take something and move it shorter distances than maybe a conveyor belt, but it can do it with greater precision. All right. There might be a machine that performs a welding operation. It can combine two pieces of metal together with a strong bond between them. Or there's something that is a press. It will go and it will use like a cookie cutter. It will chop out from raw materials into a specific shape using some sort of malleable material like steel or like aluminum. And then there's also a press. Well, I think I used the word press. That's actually a stamp. The press is what will actually then take that shape and then bend it and push it and shape it and mold it until it has some texture and it has some three-dimension to it. All right. So there are different types of machines that we would depend on to perform different actions. And the need that we might have is in a specific context might be that we need to move the raw materials from one area, like the loading dock, and put it into the press. So we might need different machines for that. There might be the need for the conveyor belt to move it the great distances. Then there might be a need for a specific machine to precisely load the raw material into the next machine that will actually do the stamping process or the molding process. All right. So there might be several machines at our disposal inside of our factory that we could use to move stuff from one place to another, and perhaps some of those machines have the capability to move it with great precision. So we're going to wind up choosing those machines that or a specific machine for the specific responsibility based on our specific need as we're designing our assembly line. So our needs might be that it must pick up one item at a time, it must tilt the item, it must thrust the item forward so that it can be accepted into the next machine. All right. And so we're relying on whatever machine we delegate this role to, all these different responsibilities. We're relying on that machine to do that millions of times without fail. It now plays an important role in our system. Now, the same will be true of objects whenever we devise our conceptual machine. There might be several different objects. Perhaps I should use the term classes when I'm talking about objects here. There's several different classes or objects that could do what we need in a given situation. Perhaps some are better suited than others in a certain situation. In that regard, there might be some interchangeability in the objects, or rather the classes, that we'll rely on to fill a specific role in our system. We choose the one that's best suited for our specific need in a given area of the system. We rely on it to do its job potentially millions of times without fail. And now that object will play an important role in our conceptual machine, in our system. So typically, just like a machine is really good at just a few tasks, maybe even just one task, An object should really be good at just doing a few things, and the scope of its capabilities should be fairly narrow focused. We might call a well-designed, very focused object highly cohesive because its entire construction, all of its moving parts, its properties, its methods, its events, they're all focused on just accomplishing one little thing, all right? So those are highly cohesive objects. Conversely, if we had a single machine capable of taking on several different responsibilities on our assembly line, at first glance that might sound great. We can save money. We just have one machine that can pick up, it can rotate it, it can stamp it, it can mold it, and then it moves on to the next part. But what happens whenever we need to maintain that machine? Is it going to be more complex to fix it whenever it breaks? And furthermore, it is aspiring to do many different things. What if it doesn't do them well? It might perform several different tasks, but is it flexible enough to do everything we'll ever need in the future? Is it possible that we've limited ourselves and we've made it more difficult to take that one machine out of our factory and replace it with smaller, more focused machines because we rely on it to do so much for us? All right, so in that particular case, we might describe such a machine as having low cohesion because, sure, it can do a lot of things, but those things are not very focused on just a small set of responsibilities. It's trying to do too much, and that might be problematic for us in the future. So in general, in object-oriented programming, we want to assign responsibilities to very focused objects that can do one thing and they do them very well. In so doing, that object will play an important role in the system. But if our needs ever change over time, it's good to know that we can swap out a given object and give it its responsibilities to a similar but different object that can perform the same role and do the same responsibilities, but just do it a little bit differently, perhaps a different way of doing business, but have very little impact on the overall operation of the conceptual system. So the takeaway is that we design objects to take on one or more responsibilities inside of our software system. Ideally, if an object can take on more than one responsibility, those responsibilities are pretty narrowly focused and we benefit from its high cohesion without sacrificing long-term maintenance and replaceability in the system. And so at this point, I just want to mention a phrase that you'll hear later called Liskow's substitution principle. The L in the acronym SOLID, which you'll hear used many times in relation to object-oriented programming. It's perhaps the most important set of principles for modern-day object-oriented programming. And so this notion of replaceability has a lot to do with how we design our objects in the first place. So in this lesson, we talked about roles and responsibilities. When we delegate system responsibilities to an object, that object now plays an important role in our system. But hopefully, it's designed in such a way that we can replace that object with a different object that can fulfill that role as well, maybe just do it a little bit differently. In the next lesson, we're going to talk about how to ensure that other objects could be called on to fill that role with a different implementation through the use of contracts. We'll talk about that next. Thank you.